And now, would you help me to welcome another Kavli laureate on stage? Her name is Conny Aerts, and here she is. Conny, you are from Belgium, from the University of Leuven.
Yeah.
And we say about you that you are a student of stars. And Conny Aerts, she has done a lot of research in the structure and evolution of stars, including stellar rotation, convection, and chemical element transport, to just mention a tiny little bit of your research. And Conny is also known as Astromama, and she might explain to us why she has this nickname. But it didn't start there, Conny, as an Astromama.
No.
You were a little girl bicycling,
Yeah.
on the way to school.
Yeah.
So please, the floor is yours.
Thank you. Indeed, I come far from the countryside in Belgium, where there were no streetlights, just sandy roads, and I was looking up at the stars all the time. And in fact, my family still says when I leave a building, I automatically look up. If it's dark, I see the stars, and if it's not dark, it's to check if it's not rainy, because I'm from Belgium, and you will understand that. So as a little girl, I was curious about the meaning of the stars in the universe, and it has been stressed so often. Please follow your curiosity. I'm going to repeat that for you, because if you're curious, then you perform better. Yeah? And if you're happy, then you're also performing better. So what my landmark is in my lab is that I like to work with students like Huda. I have a lot of students. I raise like also more than 100 master or PhD or postdoctoral fellows. My landmark is that I work as a team, you know. And that was triggered by my main discovery. I wanted to know how stars work. And at that time, that was really pure curiosity in the primary school and at your age in the secondary school. And the inner workings of stars are now tremendously important, thanks to new discoveries that weren't made yet when I was a student. You know, stars determine how galaxies evolve chemically, how material is made of. Feel your hands, your hair, your jewelry for the women, right? And for the men, because I don't want to think stereotypically. It's very important for me not to do that. All these materials are made by stars that explode as supernova and leave black holes or neutron stars. Isn't that fascinating, you know? And how stars do that was a curiosity I had. Supernovae and black holes were known when I was a student. What was not known was the existence of exoplanets. They were only discovered in 1995. And now what I'm doing daily is hunt for extraterrestrial life that may be on those planets. And a survey about 10 years ago across the world of school kids your age, near 15, yeah? Black or white, poor or rich, globally, the students raised, or they tick marked, they had to do a quiz, right? What's the most important, interesting question for you? And the winner question of all these boys and girls was, is there extraterrestrial life? And so you can answer that question. I trigger you, because your generation is going to find the answer. I am going to be a little bit too late, I am afraid. And I will tell you why. Because we know exoplanets exist. There are thousands of them, billions of them in our galaxy. Yeah. And stars determine how planets are formed. And they determine if there may be life. Our sun has decided that for us. And the sun is a star, right? Now, before you can know the answer, you have to really understand the inner working of the star, the physics of the star, and that's what I love. That's what fascinates me. And the fact that we can do that was sort of triggered by what I call my main discovery. I have a particular star that I feel very close to. And to understand it, it took me 21 years. You heard Buddha say 5 years. I gave myself, well, actually, I didn't know how many years it would take, but I had the fascination, like, I am going to understand that star. Why that star? Well, my supervisor, who taught me how to do observations in telescopes, he had been monitoring this star for 10 years, and he couldn't understand it. Now, what is so special about the way we try to understand stars? I am an asteroseismologist, aside from an astromama. And an asteroseismologist is somebody who studies star quakes. You know, I'm sure you know all about earthquakes. And earthquakes allow seismologists of the planet that we live on to deduce what type of physical processes and chemical material sits inside our planet, deep in the core. I cannot start drilling a hole here and test that experimentally because I will not make it deep enough, right? But the quakes, the earthquakes, they create waves, and these waves travel inside our planet, bounce back when they reach the core of our planet, and then seismographs can measure it, like, I do that, but then for stars. Because we live in an era where we have space missions that are operating far beyond our Earth atmosphere, and we can measure via satellites starquakes, and they do the same, up and down motion. And these are tiny little motions of the gas that make it, you know, become a little bit brighter and dimmer and brighter and dimmer. The sun also does that, but our eyes cannot capture that because it's such a tiny vibrations, and so our eyes cannot do 1 part per million precision. Yeah? That's what we need to study starquakes. And why do I study starquakes? Because I know that starquakes are the only way to look deep inside the star. And that's where the life of the star is being arranged, right? And so what we didn't know about stars until like mid-90s was how they rotate in their interior. Yeah? And rotation determines the life of the star. And so we can only do surface rotation. If you look at the sun, it has dark spots, right? And let me do a quiz. Who of you knows how fast the sun rotates around? Any idea? I don't want you to go and Google it. Just spontaneous. Nobody of you knows this? That's fine. I'm not doing it. Oh, you know. Oh, but you're not so... I'm a teacher. Yeah. I thought like, oh, how many days?
Roughly 27.
27 days. Good. Isn't that a hole in your culture that you didn't know that? Well, you can experiment it in school by the day. That's a fun experiment. Now, that's very good of your teacher. But now I will ask you a follow-up question. How fast does the sun rotate in its nucleus? Who knows that? Any guess? Awfully quiet right now. Okay, that's courageous. Okay, just shout.
1 day.
1 day. Who votes for more? Who thinks slower rotation? Raise your hands. It's not an exam, just raise hands. Who thinks it rotates faster? Okay. I will tell you something. I do not know the answer to that. So I'm not expecting you to know the answer. But I do know the answer of that same question. How fast do stars rotate at the surface and in their interior, where they do nuclear fusion. I know the answer to that question for about 2,000 stars, other than the sun. Thanks to star quakes. I find that still amazing every day. And the first star where we found the answer is my star. After 20 years. Yeah? And that particular star is a blue, big, massive star that will explode as a supernova in 10 million years, more roughly. And it has a 4 times faster rotation in the inner part than at the outside. It's thanks to star quakes that we could measure that. You know? How can you make an analogy? Well, star quakes create sound waves, right? And sound waves stay inside the star. We can't hear them, but they bounce back at the stellar core, right? And if I use the analogy with music, are there any musicians in the audience? Raise your hands. A few. But you all know, if you play music, and if you have a beautiful symphony that you train very well, but if you play it in a concert hall like this one, on a podium that is a bit more fancy than this one, and the podium starts rotating, then the musical symphony is screwed up. It's horrible. It's a beautiful experiment to do. Huh? We can't do it here. Why is that? Because rotation shifts the frequency of the sound waves, right? And so by measuring the shifts of the frequencies of star quakes, I can determine that for stars that are billions of kilometers away. Now we know how to do that, and we don't have to wait 20 years. Because if you discover it in one star after 20 years and you have a career of about 50 years, you don't want to repeat the experiment. Satellites do it for us for thousands and thousands of stars. But we don't know in advance which star is the more interesting one. And so I work with a team of students who are fascinated by that, and we all work together. When I discovered this for one of these stars, that was my eureka moment, and I discovered it in a Christmas break, because that's typically when I am among the family, and I have some peace and quiet, and I just do my nerdy data analysis on my laptop. And I discovered that shift. Yeah? I remember it very well. My daughter was there, and she is here today. She doesn't like me pointing at her right now, but I think she still remembers that. Yeah? And she said, what a kind of crazy, nerdy mother do I have, to spend data analysis in the Christmas time. But anyway, that's just to say that I didn't know if I was going to need 5 more years longer measurements, because these data were gathered from telescopes on Earth. It was before we had satellite. I didn't know if I would ever find any rotational measurements, because we didn't have it, not even for the sun. So why would you be able to do that in a distant star, right? Now we can do that pretty well, standardly. And we have discovered that the way we thought, you had a quiz, like some thought, 1 day rotation is way faster than 27 days, right? And some stars, most stars actually have fairly similar rotation in the surface that we can measure from these dark spots, and in the interior that we can measure from the star quakes. And why is that important? I'll try to explain to you, because if you like drinking coffee with milk, for instance, right? What do when you pour coffee in your cup? You pour the milk, and then you don't wait, because by the time that the milk is mixed, chemical mixing, the coffee is cold. It's not good. So what do you do as a human being? You take a spoon and you stir, right? In my language, I'm telling you that you are bringing angular momentum into the coffee by giving it rotation. So what does that tell you? Rotation gives mixing of the chemical elements, right? And if you mix chemical elements in a star close to its core, where there is nuclear fusion going on, then you bring more fuel to the nuclear reactor, so to speak. and then you can live longer as a star, right? So stellar life is determined by inner stellar rotation. And I find that fascinating. As a little girl, I wanted to know what the meaning is of stars. And that meaning has evolved. Gravitational waves are emitted by stars, supernovae, but also exoplanets are formed, and perhaps life on them. But in order to predict how that works, we need to be able to give an age to the stars. And so aging is coupled to chemical mixing, and chemical mixing is caused by inner rotation. Not the rotation at the surface, but the inner one. And that's what I study every single day. And so my motivation and curiosity is critical. But what I'm most proud of, and maybe that's a bit similar to what Huda said before me, if they ask me, I am by far most proud, except for that one star where I did the initial discovery, of my students. Because since I made that discovery, which was a kind of nice for me, I sensed the joy of being able to find something after 20 long years. And ever since that day, what I have done till the present day, and that I will continue to do until I retire, or, well, I will probably never retire, but anyway, I'm doing my hobby. Every single day, I give my best ideas and my most fascinating questions, I give them to my students. And they have made major discoveries, which I haven't been able to coach from the sideline, just to guide them. So teamwork for me is a very, very critical aspect. And teamwork is also what we do at home, and that brings me to round off to the Astro Mama, because I wanted to be an astroseismologist, but also a mother of children, to be combined with my partner is also an academic. We both studied mathematics as a startup, but we also wanted to have children, and I wanted to raise the children by myself, together with my partner. That's what we did. We were very often away. Our children were very much in the daycare, and my daughter objected several times. But I think she's still laughing at me every single day. So you can do that. And so I had a constant battle between work-life balance, being a mother in astrophysics, hence the name Astro Mama, and an astroseismologist, which is my hobby. And I still try to combine that. So for all of you, whether you are men or women, please go for your hobby. Please go for your curiosity and never, ever, ever give up, not even after 5 years. There I will stop and I'll take some of your questions.
So that was happiness,
Yes.
curiosity,
Yes.
and serendipity.
Yes.
That makes it wonderful scientists.
Yes.
Thank you so much, Conny. So, which hands do we see now? Two there, Aina, on that right row, facing us.
You said you were searching for extraterrestrial life. I also have a follow-up question. Are you searching for carbon-based life?
That's a very good question. The question is search for extraterrestrial life. That's the dominant question. Everybody wants to know. If I then talk to biologists, because this is, we only have one experiment that succeeded. That's us here, right? And so here, carbon-oxygen-based life is what comes to mind, water. So these are the elements that we would like to try and find in other planets. So indeed, carbon is a very good tracer, and oxygen and water. And so what you have to do to find the answer, and that couples back to why am I saying that you can find the answer? We are now building a space mission, a bigger one than the ones that were operational to find exoplanets by the European Space Agency. Sometimes I call it my third baby, because I helped design it. It will get launched in 2027. And that big machine will hunt for hundreds of thousands of exoplanets. But then we will know where they are. In order to come to your question, we need to be able to find the chemistry of the atmosphere of these exoplanets. And we cannot directly measure that. We can measure that when the planet passes in front of its host star. And then we have to build another space mission with detection capability of carbon and oxygen. And that's also in the planning. ESA is working also on that second follow-up mission. It will get launched in 2028, 2029. And it will get its first data of chemical tagging of exoplanetary atmospheres, like, 2035, 2040. You can do this.
Thank you.
Please go for it.
And the lady next to you had a question too.
What is the biggest star you have worked on?
Oh, the biggest star I have worked on, where we have detected star quakes, has 25 times the mass of the sun, right? And is going to explode very soon. Very soon means in about 5-6 million years, right? We cannot wait and do the experiments. It will explode and it will leave behind a black hole. Yes? So black holes are fascinating for everybody too, but the black hole is extremely simple compared to a star. A black hole is characterized by two numbers, the mass and the spin axis. That's what theoretical physicists want to get from us astrophysicists. While young stars, they have a very fascinating thermodynamics and mechanics and all sorts of quantum physics. But to come back to your question, so far we have managed to detect star quakes in blue, we call them blue hot massive stars, but only of 25 solar masses. Now there are many, many more massive stars in our galaxy, but we haven't found star quakes in them yet. And why is that? Because the more mass, the more gas a star has, the stronger its stellar wind. It blows away material. So it blows away material in our line of sight as observers. And that wind, stormy weather you could call it, is preventing us from detecting the tiny little quakes on the surface. So we are trying our best to go to higher and higher mass, because then we come closer and closer. The higher the mass of the star, the more important it is, and spectacular in terms of explosions and in chemical evolution, creating elements that make us human beings.
We have another question here, and shouldn't we challenge this
Yeah,
part?
yes.
They're coming, yeah. But first this gentleman. And we have one in the middle, and then you.
Where did I put?
Okay.
I was just wondering, the first star that you ever worked on,
yeah.
how many light years away is it?
Oh, it's several parsecs, light years away, about 100.
100 light years away?
You cannot see it by your eye. I will give you we catalog stars. It's HD 129929. That's our V836 Centauri, if you want to have its name. Yeah. So luckily for us, it has about 10 solar masses, 9.5, and as I said, it will explode as a supernova, but not in 10, 15 million years. But we don't have such stars of that mass close to us. So in our close environment, close to me as an astronomer, yeah, it means like up to several tens of parsecs, yeah. And if you want to know, we express it in light years, astronomers. We like big numbers, huh? Because kilometers is not convenient. Because the closest neighboring star to us is Proxima Centauri. That's a 4 with 13 zeros if you express it in kilometers. I cannot even explain the number in a word. So that particular star is like more than 100 times more away even, right? So that's very far for human beings, but still very close for astrophysicists, okay?
And how is it that we've found the rotational speed of the nucleus in that star, but why have we not found it in our sun? Is that not...
Excellent question. Why can we deduce the inner rotation of that star and not in the sun? I will tell you why. Because stars have all sorts of star quakes, but we need specifically dedicated star quakes that probe the deep interior. Some quakes just probe the outer layers of the star and go only 10% inwards, but I need quakes that go 90% inwards, and the sun doesn't have such quakes. The sun does have solar quakes, helioseismology, but they don't travel all the way to the interior of the sun. So we will never know it for the sun. Unless we find new tools to sort of have better detection capability. There are all sorts of star quakes, and you need the good ones to go to the deep interior. Yeah? And so I know now which stars have good quakes and also still good but less good quakes.
Does that have something to do with the size of the star, or...?
Yes, it has a lot of... you should come to my symposium. Or watch my lecture on YouTube.
There is an Astro symposium on Thursday. You are invited. Yeah.
Thank you.
And the gentleman behind you has... Please, I tell you a secret. I know that Conny would like to change into a dress before she meets the king. So we have to sort of have exact questions. You know the time when you have to leave.
Well, I'm following Eirik. He's the boss.
All right.
He decides.
But please, your question.
Yeah, you said you were looking for exoplanets for extraterrestrial life.
Yeah.
Why are they so important? And what's the difference between an exoplanet and a normal planet?
Well, a normal planet, I guess you mean us, like in our solar system. So our solar system has several planets, but it's just one system revolving around a simple star like this. The sun, for me, is just a simple, quiet star. Luckily for us. That's why it's pleasant here for humans, right? But there's a whole variety of exoplanetary systems, very, very different from our own one. So before they were discovered in 1995, we thought that we were just like all other possible planets there could be. But this is not true at all. You have very big planets close to the central star. You have very distant planets revolving very cool stars, red stars as we call them, and then much bigger, hotter stars. And so if the star is hotter and bigger, then to find life, you have to be further away because the temperature for water has to be in the habitable zone, as we call it. So we have a whole variety of exoplanetary systems that we had not at all anticipated as astronomers because we were living on the one experiment and we thought that's it, you know. Yeah?
What's the technical definition of an exoplanet?
You are also invited to the symposium.
An exoplanet is a planet around a star other than the sun. Okay?
Shall we take a final question here, Conny?
Yeah.
Would it be more interesting for you to find alien life or alien ruins? And
or
why?
alien
ruins?
Okay. Equally interesting because to make it clear to you, in about 4.5 billion years, the sun will expand as a red giant and it will swallow us. Right? You don't have to worry about it. Not even your great-great-great-grandchildren have to worry about it. But life comes and goes. Yeah? It's not because life on Mars is now no longer obvious that it has never been there, etc. Yeah? So even finding forms of past life is equally interesting to understand current life, because it's a whole history in the 13.8 billion years of the universe, in fact. Yeah? Now, to find active life via atmospheric censoring is going to be much easier than to find former life, which you actually have to look and do some geology, and we can't do that on exoplanets, okay? So any form is welcome, but it will be easier to find currently active life, okay?
Thank you so much, Conny. That was really a thrill.